So at the end of class on Wednesday, we were talking about a conducting cube, a large conducting cube. We're not worried about the edges. We're near the middles, and we'll just say that the charge density is sigma, and it's constant everywhere. It's not actually constant everywhere because it's going to be bigger closer to the edges, but as long as we're near the middle, we're okay. And we'll just say that the charge density there is Q over A. And I asked, what is the field near this surface? And we had just calculated that the field near a plane of charge where you have field on both sides is is sigma over 2 epsilon 0. We had calculated that previously also for a plane of charge, but this is not a plane of charge. This is a conducting solid. And the difference is that think about the two sides of the plane. Outside the conducting solid cube, there is an electric field, but inside the conducting solid cube, there is not an electric field. So I'm going to go to another page and draw a plane of charge. So this shows a plane of charge, excuse me, and the electric field, I forget where I was, but the electric field due to a plane of charge at any point above or below the plane is sigma over 2 epsilon 0. The difference between that and the solid conducting conducting cube or solid conducting surface is that the electric field only points outward from the surface and there's no electric field on the other side. So if we then apply Gauss's law, let's draw a Gaussian surface. Let's draw our Gaussian cube. There's only electric field through this top surface of the Gaussian cube. There's no electric field through this bottom surface like there was for the plane. So what Gauss's law ends up giving us, I've written down Gauss's law here, the flux through the cube, there's only flux through a single side now. So we've got the flux through the single side, the dot product goes away like usual, the integral goes away like usual, and we've got E times A equals the charge enclosed in the cube, which is still going to be sigma A over epsilon 0. And so therefore E is equal to sigma over epsilon 0. Whereas for the plane of charge, remember, we had sigma over 2 epsilon 0 because for the plane of charge, when we applied Gauss's law, I'm going to write up in the left-hand corner, we had the flux through the cube was equal to E times 2A because we had two areas of the cube in which the the field went through. So the field near a conducting surface is different than the field near a plane, a conducting cube, a conducting volume is different, is twice as much as the field near a plane of charge, and that shown by Gauss's law. I don't think it's obvious at all, but what that does tell you is that the charge distribution, the amount of charge, the way the charge is set up on the surface is different for a conducting, the conducting solid where the charges all move until the field inside cancels, right? The charges all move until the field inside cancels, so the charges are going to be distributed differently than for the solid cube than for the plane, because for the plane, they're not all moving until some field cancels somewhere. They're moving certainly until they're in equilibrium, but it's just a different situation. It's a surprising result, I think, at least sometimes it's surprising to me, but that the field near the surface of a conducting volume is sigma over epsilon 0. It's twice as much as the field due to a plane of charge. Okay, I've annotated these pictures just a little more, but hopefully you can just see the difference that the electric field of the plane goes through two surfaces of that cube, and the electric field of the conducting cube only goes through one surface. So we're going to have a different electric field outside the conducting cube than the plane of charge. So how do you know that glass is... Whoops, that was a good way to screw up a joke. But anyway, how do you know that... Okay, I'm trying some editing here, which I'm not sure how it works, and it doesn't let me go back and check to see, but I think I deleted what I was trying to say earlier about a bunny joke. But if you got part of it, don't worry about it. So instead, I'm going to do another one. The lion, the king of the jungle, decided to have a party. He invited all the animals in the jungle, and they all came except one. Which one didn't come? The giraffe, because he's still in the fridge. Okay, I guess I should tell the bunny joke now that I mentioned I had a bunny joke that I was starting, and I screwed up. How do you know that carrots are good for your eyes? Because you've never seen a bunny wearing glasses. Okay, so now we're going to start the potential energy chapter, the potential chapter, electric potential. But in general, we know all about potential energy. We've done it many times, right? It comes from the fact that the work done by any force is defined. The work is defined as being done by a force, and it's F dot D times some distance variable. F dot dx, if you want to call x your distance, or s if we got some arbitrary distance variable. And remember, that's you have something that goes along a path, let's say a distance s, and we pull with some force F, and there's some angle between them, and so therefore the work is the integral of Fs times the cosine of the theta between them. And if F is a constant and S is a constant, then it's going to just be Fs cosine theta. Or if F varies, we got to actually do an integral. If F varies with S, with the distance. Again, we could call, oops, that was supposed to be a ds. We could call S the x direction and just say F dx. In any case, that's the definition of work done by a force. So then we said that if the force is conservative, right? Do you remember what that means? Think about it. So if the force is conservative, then that means that the work done is path independent. It only depends on the starting point and the ending point. Like for gravity, the work done by gravity only has to do with how far you've moved in the vertical direction. It doesn't matter what path you've taken to go from, let's say, the top of the building to the bottom of the building. You could take an elevator, you could take the stairs, you can go down one stairwell, up another stairwell, and down the elevator. But the work done by gravity is only going to depend on your starting point and your ending point. If you've gone down, the work done by gravity is mgh, where h is the distance that you've gone down, regardless of how you got there. That's what it means to be conservative, that the work is independent of path. And if it is independent of path, we can define a potential energy, and we define it as minus the change in potential energy equals the work done. So if the work done is positive, then the change in potential energy is negative. That's all it says. And if the work done is negative, then the change in potential energy is positive. Think about lifting an object up from, let's say, h equals 0 to h equals h. You know, a y equals 0 to y equals h, maybe we should say. And we lift something up. The work done by gravity is negative. Is going to be minus mgh because the gravitational force is down and the distance is up. So the work done by gravity is negative, but we say that the potential energy is positive, or the change in potential energy is positive, right? The change in potential energy is plus mgh. Or if we define the potential energy equals 0 at the bottom, then we can just say U is equal to mgh, but that's where we had to define our 0. Remember that? About the potential energies. So this is how we define potential energy. I'm going to put a third equal sign there because that's how potential energy is defined. So I'm going to write a general... Oh, my bunny just showed up again, so I'm not sure how that works. But anyway, okay. So from the definition of potential energy, we get change in potential energy is minus F dot D position vector. That's a definition of potential energy. And we use that to show that if the force is constant, like for gravitation, then the change in potential energy is mgh, where h is your height that you're moving through. We showed for the gravitational force, when the force was not constant, that the change in potential energy... sorry, hold on. Okay, so try again. So we calculate using that definition of potential energy that the potential energy due to gravity is mgh when we're near the surface of the Earth, where we can assume that the force is approximately constant. And that does mean that we're defining the potential energy equals 0 at h equals 0. We always have to define it. That's because of this change in. We always have to define it relative to some place. And then we found that the potential energy due to gravity, when we cannot assume the force is constant, when we get farther from a planet's surface, for example, is minus gmm over r, where r is the distance from the center of the planet, say, for example. So we've used this definition of potential energy in order to calculate those potential energies. We also have the potential energy due to a spring is equal to 1/2 kx squared. Again, that came from integrating the force kx dotted with x, and we integrate kx squared, kx dx, and we got 1/2 kx squared, and that's relative to the potential energy equals 0 at x equals 0 when the spring is unstretched. So we can use this to calculate potential energies of anything that's conservative, and we find that the electric force is also a conservative force. You can think about that the work done by the electric force, again, only depends on endpoints, so we can define a potential energy due to the electric force. So since the electric force looks a lot like the gravitational force, the potential energy due to the electric force between two charges is going to look a lot like the potential energy due to the gravitational force between two masses. But there is going to be a negative sign difference, because the electric force between two positive charges is repulsive, whereas the gravitational force between two positive masses, and mass only comes as positives, is negative. So there is going to be a negative sign difference. So this is the way we calculate potential energies. We have to integrate from one position to another position. The initial position, remember, is where u equals 0. And the final position is the position of interest. What is the potential energy when, let's say, 2 point charges are separated by a distance r? Now, the question is in this situation, where is the potential energy equal to 0? We've already discussed this for masses, that the place that the potential energy is equal to 0, the place that there is no potential energy due to the fact that they are in the vicinity of each other, right? Potential energy means you let it go, it gets some energy. So the place where the potential energy is 0 is infinity. So at r equals infinity, therefore u equals 0. So we need to integrate from infinity to r. So when we're filling in, so the potential energy, or the change in potential energy when we go from where u equals 0, r equals infinity, to r, to a distance r, where there are two charges are a distance r apart, is given as the formula that I've written down here. There is a subtle point here, which is what happened to the dot product. Well, if the force is outwards and dr is outwards, then the angle between those is 0 degrees, and so the cosine of theta, f dot ds, or f ds cosine theta, which in this case is going to be f dr cosine theta. Theta is 0 degrees, so cosine theta is 1. And so the dot product just goes away, or doesn't go away. The dot product is just going to be f ds times 1. And the subtle point here is that a student who is astute might note that the force is a repulsive force, so the force is away. If we're looking at the force on Q2, say, for example, the force due to Q1 is away, and the force on Q1 is away from Q2. Those forces are away. But if we're moving these two charges towards each other, you might ask, isn't dr opposite df? Because we're moving the two charges from infinity to r. And indeed, it is opposite df. opposite F. But we don't use theta of 180. Again, this is a really subtle point. You don't use a theta of 180 because the negative sign comes in from here. Whoops. The negative sign comes in from here. It's the fact that we're integrating from infinity to r. That's what makes dr negative. So we treat dr like it's a positive radial direction, but it's the limits of integration that make dr turn around and become negative. So these limits. So if we had put in a minus dr instead of a plus dr, we would have been doubling the negative when we should only have the negative sign come in because of our limits of integration. It's a very subtle point, but it's an important one regardless. The potential energy that we get for 2 point charges is given by this formula, and then we can go ahead and integrate it. Okay, so let's do this integral. We've done it a million times before. The integral of k q1 q2 over r squared dr. We're going to pull, and there's a minus sign out front. We're going to pull the k q out. Minus k q1 q2 integral of dr over r squared, integrating the limits from infinity to r. Because again, we're bringing two charges from far apart to a distance r from each other, k q1 q2, and minus, and the integral is minus 1 over r, evaluated from infinity to r, which is the two minuses cancel, k q1 q2, 1 over r, evaluated from infinity to r, which equals k q1 q2 over r, that's evaluated at r, minus k q1 q2 over infinity, which is 0. 1 over infinity is 0. Anything over infinity is 0, except for infinity over infinity. So therefore, delta u is equal to k q1 q2 over r. Nothing new here, right? This is exactly the same as we saw with the gravitational force. Except the difference is a minus sign. And the minus sign physically makes sense because with the gravitational force, it was an attractive force, and this is a repulsive force. So with the gravitational force, the potential energy went down as they get closer together because they want to be closer together. Whereas here, the potential energy goes up as the charges get closer together because they don't want to be closer together if they're two plus charges. Note that if it's a plus and a minus charge, if Q1 is positive and Q2 is negative, then delta U ends up being negative k Q1 Q2 over R, where Q1 and Q2 are the absolute values of the charges. And so then it's just like gravitation, where the attractive charges want to be closer together, so the potential energy goes down as they get closer together, the minus sign. Okay. So this is the result. Notice I got rid of the change in potential energy because we're always going to be comparing our potential energy to the potential energy at infinity. So we're defining our zero. Our zero is u at infinity equals 0. And by defining that, we can change our we can write the potential energy at a position r. If potential energy defined as 0 at infinity, the potential energy at a position r is kq1 q2 over r. So this is the electric potential energy of two charges in the vicinity of each other. Remember what potential energy means. I know I've already said it 2 or 3 times, but what potential energy means is that they've got the potential to get kinetic energy. So these two charges, which are some distance r away from each other, if I let them go, what's going to happen? They're going to move apart from each other and they're going to get kinetic energy. So they've got potential energy, and that potential can be turned to kinetic. If I were to let these two charges go, and let's just take these two charges and let them go, say that the only force on them is the electric force from the other charge, then Q2 is going to move in this direction, Q1 is going to move in this direction. They're going to increase in kinetic energy and decrease in potential energy, because as R gets bigger, the potential energy of the couple is going to get smaller, and that's because the kinetic energy is getting bigger and energy is conserved. So notice also that this is for point charges. This derivation is for point charges. And if we want to know what the potential energy of something in a different situation is, we're going to have to recalculate the potential energy for that different situation. Sorry, I got interrupted by the phone. But I was saying that this is the potential energy, this being this formula here is the potential energy of 2 point charges, okay, in the vicinity of each other. But if I have a point charge in the vicinity of a different kind of field, then I've got to figure out the potential energy by using the definition of potential energy and integrate whatever new force there is, right? So if it's the force, for example, between a charge and a plane, right? If this is a plane, then we know that the force between them we have figured out is the force between them is QE, and the electric field that the point charge Q is in is the electric field of the plane, that's sigma over 2 epsilon 0. So the force is Q sigma over 2 epsilon 0. And if we apply the definition of potential energy, now our force, right, our force is a constant because it's not dependent on position, so it can just come out of the integral. And then the change in potential energy is going to be change in potential energy for a point moving some distance near a plane is going to be minus the force, Q sigma over 2 epsilon 0, times just the integral of the distance, which is the change in distance, delta x. So what that means, so this is the potential energy of a point near a plane. It's actually the change in potential energy of a point near a plane if we move that point some distance delta x. So if I move it delta x closer to the plane, we are going to increase the potential energy. Whoops, I made a mistake. I have to be moving it farther away from the plane. I got to be moving it farther away because by definition of the dot product, right? So the force is this way and delta x is this way. So that's when the dot product is the angle between them is 0 and the cosine of 0 is 1. So f dot dx is fx cosine theta, and that situation is when the displacement is away from the plane. So in keeping the signs consistent with what was on the previous page, delta x must be away from the plane. So as I move away from the plane, the potential energy gets smaller because there's a negative sign here, right? The change in potential energy is minus Q sigma over 2 epsilon 0 delta x. I just rewrote it here. Not sure why. And so that comes from, again, applying the definition of potential energy. But what to notice is you might say, oh, look, that's a complicated new formula, but it's not. It's really the same formula as we had for the potential energy of a mass near the surface of the Earth. When a mass is near the surface of the Earth, and it's in a constant field, right? It's a mass. Think of this as the equivalent of mass, and this is the constant field, delta x. This is the same as mgh, right? H is the distance that we move. The minus sign just indicates that the potential energy gets bigger as we get closer together and smaller as we get farther apart. And that's something which you can figure out qualitatively or quantitatively by plugging into the formula. But this really is just mgh. It's like a mass in a constant field. It's a charge in a constant field. So for a constant electric field, right, delta U electric for a constant electric field is going to be minus QE delta X for a constant electric field. And that's a general result, where if the constant field is a plane of charge, then it's sigma over 2 epsilon 0. But that's our general result, just like mgh. So we can write down potential energies for different configurations, and we'll do some more of them later on. But this is good for now. We have for 2 points and for a point above a sheet of charge, we figured out what the potential energy is. Oh, and then you can ask, well, why are we writing delta U here? Why don't we write U? Now think about it. In this case, delta U is relative to where U equals 0, and this is just a constant field. And with the constant fields, just like with the gravitational field, when we had a constant field, we didn't have to define our U equals 0 anywhere in particular. You can define your U equals 0 wherever you want. So for the constant field, this is a more convenient definition. Delta U is equal to minus QE delta X. And you just say U equals 0 wherever our initial position is, and U equals something, whatever it is, wherever our final position is, as opposed to the spherical charge density or the spherical mass density, where we chose the potential energy equals 0 always at r equals infinity. In this case, U equals 0 wherever you want. We don't have to choose the convenient, wherever you want. We don't have to choose the convenient distance for the kq over r where U equals 0 at r equals infinity. In that case, that was really the convenient choice. Here, there is no convenient choice. You can choose U equals 0 wherever you want. So this is a summary of the results that we just figured out, that the potential energy of 2 point charges in the vicinity of each other, and the change in potential energy for a charge that's moved through a constant field. And which direction is it moved? It's moved in the direction of the field line. So if it's moved in the direction of the field, if the charge Q is moved in the direction of the field, the potential energy should go down, hence the minus sign in the change in potential energy. So that's where delta X actually has a direction associated with it. Remember that potential energy is not a vector, but in order to figure out whether potential energy is positive or negative, we have to associate a direction with delta X. Just like we always said that the work done by gravity is positive when an object falls. The potential energy of gravity is positive when we lift an object up. So there's always a direction associated with the distance that we're moving the object in order to figure out whether the potential energy is positive or negative. So that negative sign is meaningful as long as delta X is always in the direction of the field. Then there's minus. And if delta X is opposite the direction of the field, then you're going to have a negative sign for delta X, and the change in potential energy will be positive. So let's do an example. Let's say that we have an electron, which is 10 centimeters, or a tenth of a meter, away from a plate, which is giving us a constant electric field of 3,000 newtons per coulombs. So if we have this electron and we let it go from rest, I want to know what's going to happen to the electron. Well, the electron is going to go towards the positive plate, and it's going to hit the positive plate. If I just let it go from rest, it's going to move, and it's going to hit the positive plate, end up here. I want to know how fast is the electron going just before it hits the plate. So in order to solve this problem most easily, we want to use energy conservation. And energy conservation, E total initial equals E total final, which is also the same as saying that the change in potential energy is equal to minus the change in kinetic energy. Oh, and I guess I've changed over to using U for potential energy here instead of PE, but I think most of you are used to U or PE or P, meaning potential energy. In any case, this is a statement of energy conservation. Delta U equals minus delta K. If the potential energy changes, then the kinetic energy changes if energy is conserved, if mechanical energy is conserved. So we're going to use this to figure out the speed of the electron when it hits the plate. There is an assumption that I said earlier, I just never wrote it down, that the initial velocity is equal to 0. V initial equals 0. So, so what is the change in potential energy of the electron as it moves the 10 centimeters towards the plate? Well, the change in potential energy is going to be minus Q E delta X, but now we got to be careful with our signs. There's two ways to do this. One is to say, hey, we know that the potential energy of this electron should go down as it gets close to the plate, right? Because the kinetic energy is going up. So the potential energy should go down. So whatever values we plug in for Q, E, and delta X, we can just plug in the absolute values and make sure in the end the change in potential energy is negative. That's fair. Just saying, look, we can figure out the sign qualitatively. Or you can be careful and go ahead and put in the minus 1.6 times 10 to the minus 19 coulombs. The electric field is positive 3,000 newtons per coulomb. And delta X is also going to be a negative number because it's opposite to the field lines, right? The field lines from this plate are pointing up wherever this electron is. This is the electric field. So remember, delta X is the distance moved in the direction of the field line. So the delta X, I didn't leave myself space, but times delta X is going to be negative 0.1 meters. So this is the potential. Being careful by plugging in all the correct negative signs, you can see that in the end we will indeed get a negative change in potential energy, which you could qualitatively argue it should be negative. Let's just put in all absolute values of the numbers and then make sure it's negative in the end, because the potential energy should be going down because the kinetic energy is going up. So now we plug in those numbers and we get that the change in potential energy is negative 4.8 times 10 to the minus 17, and the units end up being Newton meters. And remember, a Newton meter is a joule. So the units work out. It looks like an awfully small change in potential energy. It looks almost immeasurably small. But remember, an electron is a very small thing, right? So delta U is equal to minus delta K, which is minus 1/2 mv final squared minus 1/2 mv initial squared. That's delta K. And V initial is 0. So this is equal to minus 1/2 mv final squared. So therefore, the final velocity of the electron, the minus signs cancel, and we get 2 times 4.8 times 10 to the minus 17 joules, Newton meters. Divided by the mass of the electron, which I just look up as look in the front cover of the book, Google it, ask Siri, 9.1 times 10 to the minus 31 kilograms, and then square rooted. So we're just solving this. We're solving for V in the equation above, delta U equals minus delta K. So solving for V, we do that algebra, and we get an awfully large velocity, 1.03 times 10 to the 7th meters per second. Whew. But, I mean, it seemed like the potential energy change was small, but the mass of an electron is so small that gets to be actually incredibly high velocity by the time it hits the plate. How big is that velocity? Not essentially important for you to understand right this second, but it is what's called almost relativistic velocity. It's a velocity that we could never have any appreciably massive body reach, a car, a spaceship, etc. To reach those kinds of velocities is something very futuristic. But in any case, that's a high velocity. It's reasonable for a subatomic particle, unreasonable for a spaceship. There, okay. There's a spaceship going at high velocity in a future time when we can get going that fast, and then that means we can actually travel through time when we can get going that fast. In any case, that's an example of a use of the potential energy due to the electric field and using that for energy conservation. So just like we have the connection between electric field and electric force, right? F is defined as QE, or that's how we define electric field, and in case E is equal to F over Q. There's a quantity in electricity that a analogous quantity for potential energy, where potential energy equals Q times something called electric potential. So V is electric potential. It's not electric potential energy. Electric potential energy is U, right? This is that's potential energy for electricity. It would be electric potential energy, right? So if we're talking about electricity, this is electric potential energy. The terminology here can be very confusing, so you've just got to know it. You've got to remember it. You've got to learn it. That U is electric potential energy. V is electric potential. Now, very similar names, but different quantities. What is electric potential? Electric potential is electric potential energy per unit charge, just like electric field is force per unit charge. So this is an analogy between E and V. If F is related to U, then E must be related to V in the same way because there's just a Q. That's the difference between the two. So remember that the concept of electric field is if I have a charge here and I have a charge here, that let's just fix this charge in place, pin it in place, tack it down. This charge is going to feel a force from the first charge. If I then say, hey, let's get rid of the charge on the right. Let's get rid of the charge on the right. Oops, I'm getting rid of my pin too. But anyway, let's get rid of the charge on the right. Let's put my pin back in my charge here. And ask, well, there was a force on the charge that was there, so what is there now? We say, hey, there's no charge there, but there was a force there, so there's something there, and we call it the electric field, right? So that's where the concept of electric field came from, that something's got to still be there. How do we know there's an electric field there? We know there's an electric field there because if we put a charge there, it feels a force. So there's something there called the electric field. It's the same idea behind electric potential energy. If we say we've got a charge here, and we pin it down, and then we put a charge here, then this pair of charges, there's an electric potential energy associated with the pair of charges, KQ1, Q2 over R. But if we get rid of the charge on the right, is there still some kind of potential there? There's the potential to give a charge potential energy. So if we get rid of the charge on the right, we say, there's no charge there, but there's still the potential to give a charge potential energy, and we define that potential again as potential equals U over Q, and that's the potential of a point in space. There is a potential to give a charge potential energy if the charge goes there. It's really a very simple concept. It's not meant to be difficult. It's if we have a point in space that's in the vicinity of other charges, we say there's the potential, if we put a charge there, for it to get potential energy. So that's the concept of electric potential. And then remember the relationship, delta U is defined as minus F dot ds. Well, if delta V is delta U over Q, then we can just divide that integral by Q, and F over Q is E, so delta V is just E dot ds. So delta V, the change in electric potential, is minus E dot ds. One last thing, and then I'll shut up for today. Delta V is change in electric potential. Change in electric potential between 2 points in space. So we talk about the change in electric potential between 2 points in space. Or it is actually called the electric potential difference. Either is okay, but the official term is electric potential difference. It's the difference between electric potential between 2 points in space. If there is a difference in electric potential between 2 points in space, think about it. What that means is that we can, if we put a charge at one point, it can move to the other point because there's a difference in electric potential energy for the charge in those 2 points. And a charge will always move from a higher potential energy to a lower potential energy. We'll talk about that later. But an electric potential difference means that you can then move a charge between those 2 points from the electric field. And this is actually what voltage is. Voltage, right? What is a voltage? We've learned in lab that a voltage is something, it's actually an electric potential difference that we put in a circuit in order to move charges from one place to another. So delta V is voltage. It gets very confusing because the units of voltage is V, but the symbol for voltage is delta V, and then we use V for voltage. But actually voltage, so we often call voltage V, but that's a misnomer. That's incorrect because V is electric potential at a point. Voltage is really delta V, but in circuits, we often just write it as V. And that's a little bit confusing to students, but you just got to know that voltage is actually an electric potential difference. And so if you see a V and somebody calls it voltage, then you know that actually means an electric potential difference between 2 points. I'm sorry I had a matchstick puzzle, but I lost it. and I really need to post this lecture, so I'll save it for next time. Okay.